ועכשיו אני חושב שצריך להזמין את פרופסור הנס ויידנמולר, והוא צריך להופיע בזום ויספר על הימים הראשונים של המודל הקליפות ועל הימים הראשונים של שיתוף הפעולה הישראלי-גרמני שהוא ויגאל עבדו על זה יחד. יעל? הנה הנס. Hello, Hans.
Thank you, Uzi. Hello, Igal. Hello, everybody. I am honored and privileged to be asked to talk to you today on this wonderful occasion. And as Uzi mentioned, I was asked to focus on two items: Igal's contributions to the early development of the nuclear shell model and to the Israel-German scientific cooperation in the framework of the Minerva program. I first met Igal almost 60 years ago in the summer of 1965 at a nuclear physics summer school held at Nijenrode Castle in the Netherlands. By that time, Igal had been working on nuclear structure theory for 15 years and had made important contributions. To appreciate the impact of these contributions, it is necessary and useful to put them into proper perspective and to take a step back in time. The atomic nucleus was discovered by Ernest Rutherford in 1911. He found that each atom consists of a cloud of negatively charged electrons that orbit the positively charged atomic nucleus located in the center of the atom. The atomic nucleus is orders of magnitude smaller and orders of magnitude heavier than the surrounding cloud of electrons. Research on the constitution of the cloud of electrons, that is, on atomic structure, governed much of the fundamental work in physics in the first 3 decades of the 20th century. That work led to the discovery of quantum mechanics. Research on the physical properties of the atomic nucleus started only in the 1930s. It was soon understood that atomic nuclei consist of two types of particles: the positively charged protons and the uncharged neutrons, both of nearly equal mass. The question was how protons and neutrons combine to yield the properties of the atomic nuclei that exist in nature, ranging from the lightest nucleus, hydrogen with a single proton, to the heaviest one, uranium with 92 protons and a larger number of neutrons. Much of the work in nuclear physics in the 1930s was dominated by an idea of Niels Bohr in Copenhagen. Bohr postulated that the mutual interaction of protons and neutrons in the nucleus is very strong. The compound nucleus, as Bohr called that system of strongly interacting particles, is a black box that has no memory. In a reaction that populates the compound nucleus, its decay is independent of its mode of formation. In view of the strong experimental support for Bohr's idea, the success of a radically different model of the atomic nucleus, the shell model, came as a great surprise. Whereas Bohr's model relates to data on nuclear reactions that lead to highly excited nuclear states, the shell model originally addressed properties of nuclei in their ground states. In 1949, Maria Goeppert-Meyer in Chicago and Hans Jensen in Heidelberg independently proposed that in the atomic nucleus, neutrons and protons move nearly independently of each other in a common potential. That idea is obviously diametrically opposed to Bohr's idea of the compound nucleus. The common potential of the shell model consists of two parts: an attractive central part and a strong spin orbit force. That force was the essential novel element in the proposal. The discovery of the shell model was triggered by strong empirical evidence for the existence of the so-called magic numbers. Nuclei had been found to be especially stable and to occur especially frequently in nature when the number of protons or the number of neutrons in the nucleus equals one of these magic numbers that have values 2, 8, 14, 20, and so on. The shell model proposed by Goeppert-Meyer and Jensen successfully accounted for these magic numbers. To see how this comes about, I have to be a bit technical. I refer to protons and neutrons jointly as nucleons. Some of the technicalities are also displayed on the first slide. Because of the strong orbit force, single particle states in the shell model are characterized by little j, the total nucleon spin, obtained by coupling the intrinsic spin 1/2 of the nucleon and its angular momentum L. The total nucleon spin has values 1/2, 3/2, 5/2, and so on. Single particle states with the same value of little j have the same energy. The number of such states is 2j plus 1. These states form a shell. Because of the Pauli exclusion principle, there can be at most 2j plus 1 protons or neutrons in a shell. Particularly stable nuclei are expected to occur when the numbers of protons or neutrons correspond to a filled shell. In this way, the shell model predicted stronger binding energies and larger abundances of closed shell nuclei and thereby accounted for the magic numbers. In addition, the shell model correctly predicted the ground state spins of nuclei that differ from a doubly closed shell nucleus by the addition or removal of a single electron, a single nucleon. The agreement of the shell model with existing data on binding energies, abundances of elements in nature, and nuclear spins was convincing, and in the 1950s, the shell model quickly gained wide acceptance in the nuclear physics community. But what about nuclei that differ from a closed shell nucleus by the addition or removal of 2 or more nucleons? In other words, what can be said about nuclei with partially filled shells? In that case, the total spin, capital J, of the nucleus is obtained by coupling together the nucleon spins little j in the partially filled shell. That coupling yields several values of total nuclear spin capital J. In the strict single particle shell model, all these states have the same energy. That is not observed. What is observed instead is that such sets of states do exist, but each state has a different energy. The qualitative explanation is that nucleons within a shell do not move completely independently, but interact with each other. The interaction splits the energies of the states with different total nuclear spin capital J. The interaction is called the residual interaction because it is that part of the full interaction of free nucleons that is not accounted for by the central potential and the spin orbit force of the original shell model. Thanks for the slide. The challenge was then to determine the residual interaction, to add it to the shell model Hamiltonian, and to calculate the resulting spectrum of states with different total spins capital J. One might have expected the founders of the shell model to take up the challenge. But in the years following the discovery of the shell model, both Maria Goeppert-Meyer and Hans Jensen were focused on refining the model by collecting additional empirical evidence for it. It was Igal who took up the challenge. Already in his PhD thesis at the ETH Zurich, written under the supervision of Wolfgang Pauli and completed in 1951. He addressed the residual interaction in the shell model. Remember that the shell model had been discovered only 2 years earlier, and you see that Igal was probably the first scientist to have a serious look at the problem. At first sight, the problem might have seemed similar to the analogous problem in atomic physics that had been treated successfully for decades. But actually, the nuclear physics problem turned out to be much more difficult. First, the form of the central potential of the nuclear shell model was unknown, in contrast to the atomic case. Second, neither the form of the residual interaction nor its strengths were known. Third, although similar calculations had been carried out in atomic physics, several forms of the residual interaction that were suggested by symmetry arguments required new theoretical methods of calculation. Fourth, experimental data were scarce. Complete spectra were rare. Spin assignments for nuclear states were often insecure. Finally, the only means available for the numerical calculations that had to be done eventually were mechanical desk computers. These were painfully slow. It took a combination of intuitive insight, theoretical arguments and calculations, and hints from empirical evidence for Igal to move forward. First, together with Giulio Racah, he identified the pairing force as an important element of the residual interaction. That force binds together pairs of neutrons or pairs of protons to particularly stable configurations. That step was the first in a sequence which I cannot describe in detail. Gradually, Igal's work shed light on the essential properties of the residual interaction. His results gained increasing attention by the international community. After his return from a 2-year stay at Princeton University, Igal built up the nuclear structure theory group at the Weizmann Institute. Soon, it became probably the strongest and most visible such group worldwide. The success and impact of the group was put into evidence at the Harvard Conference on Nuclear Structure, held in 1957 at the Weizmann Institute. Here, results were presented and discussed at an international forum. Hans Jensen attended the meeting. He was the first German scientist to be invited to Israel. I remember his report of the meeting to us, his PhD students. I remember even more vividly his impressions of the new state of Israel. And I remember strongly how touched Jensen was by the friendliness and care shown to him, a German, 12 years after the Holocaust, not only by his colleagues, but also by nurses and doctors, complete strangers to him, when he fell ill and had to receive hospital treatment. In the following years, Igal continued to make important contributions to the shell model and the residual interaction. He became one of the founders of theoretical nuclear spectroscopy. His contributions are here to stay. Later, he took up an important second independent problem of the shell model, brought to light by the discovery of the collective model in 1953 by Owe Bohr and Ben Mottelson. The common mean field potential of the shell model is not static. It represents the average interaction of each nucleon with the remaining nucleons, and is therefore a dynamical entity in its own right. It may deform and undergo oscillations. How to combine such collective nuclear motion with the single particle aspects of the shell model is the second big topic of Igal's work. That will be addressed today in the talk by Franco Iachello. Let me now turn to Igal's role in the Minerva program. I begin again with the history. After the foundation of the State of Israel, diplomatic relations between Israel and the Federal Republic of Germany did not exist. There were only very limited contacts between the two countries. The Holocaust was too heavy a burden. The Minerva program was initiated with the aim to overcome the speechlessness between the two peoples. Scientific contacts were thought to be a first step towards a full dialogue. In 1956, a Weizmann scientist, Gerhard Schmidt, an emigre from Germany, took the initiative and approached Wolfgang Gentner, a professor of physics in Freiburg, Germany. The role Gentner had played in occupied France during the war had shown that he was a man with integrity. Schmidt and Gentner talked about ways to bring scientists from the two countries together. These early contacts were deepened in talks between Wolfgang Gentner on the one hand and Gerhard Schmidt, Amos de Chalit, head of the Department of Nuclear Physics at the Weizmann Institute, and Joseph Cohn, European representative of the Weizmann Institute, on the other. The talks took place in Geneva, where Gentner served as one of the directors at CERN, the European Center for Research in Nuclear Physics. These talks and support by Ben-Gurion, Prime Minister of Israel, and Konrad Adenauer, Chancellor of the Federal Republic, led to a visit in Israel of a group of scientists of the Max Planck Society, led by Gentner, and in its wake, to the establishment of the Minerva program for German-Israel scientific cooperation. The program envisaged the exchange of scientists between the two countries, supported by funds for travel and for their research work. The Weizmann Institute was the first institution of higher learning in Israel to open itself to the program. Whether or not to accept scientific visitors from Germany was a highly controversial issue. It became even more so when the Eichmann trial started. The question was decided separately in each department. The nuclear physics department of the Weizmann Institute was the first to take that step. That was due in part to the influence of Amos de Chalit, chairman of the department and later head of the Weizmann Institute. The first young German scientists, theoretical physicists, arrived in 1961, each for a stay of a few months. At the same time, a committee, the Minerva Committee, was set up to supervise the program. It consisted in equal parts of Weizmann scientists, Amos de Chalit among them, and German scientists. Wolfgang Gentner was in the chair. For the first 10 years, the Minerva program was lopsided. Young scientists from Germany would come to the Weizmann Institute for visits of 1 or 2 years, but only senior scientists from the Weizmann Institute would come to Germany for brief visits. I remember talks given at Heidelberg University in the 1960s by Amos de Chalit, Harry Lipkin, and several others. It was only in 1968 that the first young Israelis from the Weizmann Institute, Israel Pecht, and today's chairperson, Uzi Smilansky, would come to visit Max Planck Institutes in Germany for an extended stay. The death of Amos de Chalit in 1969 dealt a blow to the program. After the death of Gerhard Schmidt, Amos had been the driving force behind the program on the Israeli side. Up to that point in time, Igal had not been part of the Minerva project. And at the time, I had the impression that he belonged to the large group of people at the Weizmann Institute and elsewhere in Israel that viewed with reservation the Minerva program and more generally, collaboration with Germany and Germans. It was all the more surprising and reassuring that, without blinking an eyelid, after Amos' death, Igal stepped in and took Amos' role in the Minerva Committee. The next Minerva Committee meeting after Amos' death took place in 1970, and you see, and Igal attended it. And on the next slide, you see Igal in front of one of the buildings of our Max Planck Institute, from where I am speaking. And the next slide, you see Igal in conversation with Hans Jensen, again in 1970 at the same meeting of the Minerva Committee. Thank you for the slides. After the death of Hans Jensen in 1973, I took Jensen's place in the committee, and I came to know Igal more closely. I got to know him as an outstanding scientist and a wonderful person. I deeply respect him. I found him totally reliable, absolutely loyal, always prepared to accept responsibility, with clear judgment and with constructive ideas. After a few difficult years, the Minerva project expanded and eventually turned out to be very successful. It had gained wide acceptance in Israel. The other Israeli universities had gradually joined the program. Today, the program finances research projects and Minerva centers. It also includes a student fellowship program. A very important part of the program are the regularly held topical meetings that carry Gentner's name. From an overall perspective, the Minerva program has given an uplift to research, both in Israel and in Germany. Germany has become the second most important scientific partner of Israel, for Israel after the United States. But the most important aspect of the Minerva program is the human one. Through years of cooperation and extended visits, scientists from the two countries have learned, first, to open themselves to their opposite number, and later, in many cases, to become friends. That is a slow and difficult process. The German partner has to face the abyss of the past. Only then can one start building bridges and develop trust. But it is a rewarding process. Speaking for myself, the fact that I have found in Israel, that I have found friends in Israel, Igal among them, is one of the great treasures of my life. And I'm certainly not the only one to say that. Generations of young German scientists have come to the Weizmann Institute and to the other universities in Israel. They have found friends, and in some cases have found spouses. These growing bonds have become possible by the humane attitude of our partners on the Israeli side. For several decades, Igal has played a leading role in this exchange. Many scientists from Germany have benefited from his knowledge, his advice, his wisdom. I'm speaking for all of them when I thank you, Igal, for all that and congratulate you on this special day. On a personal level, Bettina and I thank you both, Igal and Hannah, for your friendship, warmth, and hospitality, and send you our very best wishes. Thank you.
On behalf of everybody, I thank you, Hans, for your touching review of German-Israeli relationships and also on the introduction to the first stages of the shell model.